For those of you who don't know me, I'm Lee Valentine. I'm the Executive Vice President of the Space Studies Institute, and this is a discussion of a research program that we have undertaken with the Department of Biological and Environmental Engineering at Cornell University. This is a slide that shows the break-even time for 3 closure options. This study was done back in 1982 when NASA was interested in mounting some long-duration missions. And it just shows that it's useful to close water early, close most of your food if you're going to have a mission duration of 5 years. And if you're going to go for longer than 6 years or so, you really should close just about everything. An example of a closed system that is completely recycling and maintains nearly all the carbon in a living system. Of course, the quantities of the various constituents of this ecosphere vary. But the important thing is that with adequate light, all the carbon will be taken up and nitrogen will be fixed, and life will go on. This is an example of a very poor implementation of a closed environment life support system, and the gross failure of this system to do what its designers intended it to do, which is to show a way to colonize Mars, was the reason that we undertook to take a more careful look at closed environment systems. We had always had the bias that it was possible to do them because we know that the Earth at least more or less does it. And the initial design constraints were that we would be able to fit the system within the volume of the Space Shuttle external tank system. The systems up to now have been operated no more than 13 months. There was an initial focus in Russia on microalgae. That has no practical relevance to food or energy considerations. The goal of this particular phase 2 study is to identify and test in experimental situations those processes that will support life in closed and sustainable systems. First emphasis, of course, is documenting the flow of water and nutrients and energy. We focus on deadlock materials, and that's something that, of course, was ignored in the Biosphere study. And we focus on biological processes that minimize this system limitation. The individual subsystems are composed of technologies including microbial biofilms, the recovery of nutrients in edible plant and animal biomass, and I would say there will be animals in these systems for a number of very good reasons. Regeneration of nutrients from deadlock material, and finally the development of a mini closed environment life support system sized to support 4 people. A mini cells would enable a codification of limits to sustainable systems that are entirely dependent on biological systems. Some of the concepts that we plan to explore in this study hold promise of solving some of the larger environmental, energy, and food problems on the Earth. Full-scale demonstration of this kind of integrated biological system could lead to energy-independent and pollution-free farms. And this really has some relatively near-term applicability to farms in the United States. It's proposed to keep the goal of long-term space flight as a focus. I would just point out that Joseph Gittleson, who did most of the work in Russia over the last couple of decades, pointed out that it may be impossible to completely close this. There may be some tiny amount of refractory material that you just can't have a good biological breakdown mechanism for, in which case you may need to use some sort of physicochemical or oxidation system. But the theoretical analysis of the problem shows that the ideal can be approached very, very closely. A goal is to develop a model that describes the fate of water and the key macronutrients, nitrogen, potassium, phosphorus, and key macronutrients, and key micronutrients, particularly sulfur and metals. Confirm the fate of carbon in the solid waste, eliminate nutrients, or estimate nutrients available to the plants from stabilized waste to generate food crops using hydroponics and soil-based systems. Improve the fundamental understanding of hydroponic root and microbial interaction with human waste byproducts. And this is a critical thing. Because understanding those systems and finding a system that can use this highly active kind of waste and stand up to it will give you a nice solution to reprocessing sewage, which is very, very important to be done in a cost-effective and rapid way. Define requirements for high solids anaerobic digestion of human and plant waste and its role in closed systems. And that's a bit different from the way things are done commonly in the municipal sewage processing business, where the processes used are aerobic and require lots of oxygen. We're talking about anaerobic digestion. Compare these anaerobic wastewater treatment alternatives to the high solids design to decide whether you want to separate the solids from the liquids or put everything together. Confirm the feasibility for the anaerobic alternatives that use minimal energy to provide high energy density and purity fuel. In our first, in the phase 1 study, we developed some processes which are now being commercialized. Unfortunately, we didn't have enough money at SSI to escape the university system, and so Cornell retained the intellectual property. I don't think we're going to make that same mistake this time. We would like also to develop optimized protein generation routes using this deadlock material in algal biofilms and in vermiculture. Document the nitrogen loss by ammonia volatilization and denitrification in the hydroponic and other plant production systems. This bullet point is a big, big deal, and it's something that folks have overlooked and have not really quantified very well. It's very difficult to avoid denitrification in sewage systems, simply because you always have small areas where there's no oxygen, and anaerobic bacteria will produce reduced nitrogen that will then convert to nitrogen gas. We also hope to plan to identify biological gas fixation options using algal films, fermentation, and soil-based plant production to replenish these nitrogen losses. And these are actually fairly hefty losses per day, in the range for the entire integrated system of about 45 grams per person per day. Goal is to codify accumulating refractory products, estimate the conditions that minimize their quantity while maximizing the mobilization and identify means of complete micronutrient recovery. Identify and perform preliminary feasibility testing on innovative concepts that may be identified as breakthrough concepts. And finally, using the quantitative data developed to estimate area and mass and energy throughput of the closed biosystem components to support 4 adults and estimate time to the full operation. The amount of area required to support one human being is variable, and it's possible to get the area down into the range of on the order of 10 meters if you really optimize your plant production system and have nutrient delivery precisely controlled. On the other hand, typically it requires 10,000 meters to support a typical American. Self-repair and self-reproduction is essential, and that's one big advantage of biological systems, because they are actually quite robust as long as they're operated within their parameters, and they do self-reproduce. Gittleson again points out that in all the years of his 3 decades of experiments in the Russian studies, they had no record of a system failure due to failure of the biological system. They were all other technical failures. It's important for us to somehow match the food inlet of the human link and the biomass regenerated within the system. That's the key thing. Luckily, people can vary in their dietary requirements and they can adapt to a non-optimal diet. But our plan is that we will produce what would be considered to be an optimal diet. We talked a bit earlier about animals in this system, and the reason the animals are there is they make the system more efficient. We can then use good ways to recover nutrients in algal films that are not directly usable by people. We can feed those to worms, and those can go to fish or to poultry, and that way increases your efficiency as well as delivering a much higher quality and more palatable protein source. As I said, we need to quantify the inedible fraction of plant biomass and make it acceptable to other components of the food chain. The second largest challenge is maintenance of biological stability. We hope to discover ways of using proper ecological controls. You have to put people in the system if you want to really test it. Almost all engineers know you can't make just one change and assume that everything else is going to be the same. While it may be possible for us to do more cycles of the system without people in it to make sure that it is robust enough to count on, people have to be included in the loop eventually. Construction of full-scale closed systems now does not make sense because of the low data rate from a full-scale system and the difficulty of performing the kind of experiments that we need to get the data that you need to intelligently design another full-scale system. And we talked a bit about microalgae. That's a nightmare from the past. The emphasis on waste treatment does not focus on conversion of the waste material to the most oxidized form, as I said earlier. Human water needs are secondary to plant requirements, so the emphasis on the water cycle is to provide food for plants, provide water for plants. And we need to consider the quantitative definition of deadlock material, its rate of formation, characteristics, and quantity in the system. The most important design limiting factor is the leakage of plant available form of nitrogen into nitrogen gas. And we have to provide for nitrogen fixation. Typically that's done by a number of physical mechanisms in addition to biological fixation on the Earth. It's done by lightning, it's done by Haber-Bosch process. A bunch of different ways to do it. The lowest energy option is biological fixation. Total nitrogen requirements, 45 grams a day. We talked about the inadvertent conversion of reduced forms of nitrogen, that is ammonia, into nitrogen gas. It may be that we really do want to have soil-based agriculture and not just hydroponics. My particular bias is that we would like to have soil-based agriculture. On Mars in particular, the creation of humus is not really a big deal as it would be in other places, because you can replace that carbon that is locked up in humus with atmospheric carbon dioxide. I would point out that the aerial requirements on our baseline non-optimized system for just using typical plant growth rates in a typical glass house in the United States go from about 180 meters squared per person for a full system to nearly 300 meters squared per person if you include nitrogen fixation in that aerial requirement. This is the breakdown of the experimental program: high-rate biofilm processes, hydroponic wastewater treatment, microalgae management, high-protein recovery from wastes. That means dilute sewage. You have processed sewage, you grow duckweed, you feed the duckweed to animals. Aerobic composting or high solid digestion, self-compressing and self-purifying anaerobic digester systems. This gives high pressure and reasonable quality methane. It does have mercaptans and maybe a tiny amount of hydrogen sulfide in it, so it is not suitable as it comes off presently as a fuel. We hope to get it closer to fuel grade methane. So here's the experimental plan and how we hope to do it. To develop the model, we need to be sure that we understand the estimates of adult requirements and how to refine those estimates. To confirm the fate of carbon from human waste and inedible plant biomass, we will operate the anaerobic treatment system alternatives on synthesized and actual combinations of waste, using several different potential candidate systems. In coupled systems, we use the waste effluent as nutrient source to further purify waste and generate mass in the nutrient film technique systems. We may consider using, we are going to think about using the refractory organics to propagate a soil-based plant production unit. We'll have to estimate carbon and nutrient turnover rates from this deadlock material and test the potential requirements of intensive treatment to regenerate the nutrients and carbon using wet oxidation or alternatives. We have a new plant that we think might be really useful to do wastewater treatment, and that is a plant called Chufa. It also produces things that are perfectly satisfactory for animal feed. We need to define the potential role of our anaerobic composting and its role in processing plant crop waste. We plan to construct and operate an anaerobic digester system capable of producing off gas at greater than 85% methane at greater than 1,000 psi without using significant energy and using low quality biomass. We need also to generate optimized protein generation routes, and we'll use coupled systems to estimate the potential to recover reduced nitrogen forms, that is ammonia, mobilized in waste treatment to valuable protein in duckweed and spirulina. These will run in parallel and in series with digestion trials of low-quality biomass and wastewater treatment. Vermiculture will be used to consider capturing the microbial protein and upgrading it to worm protein. We need to operate our nutrient film technique hydroponic production systems with attempts to measure nitrogen balance, and we'll use two separate plant species. One that is known as hardy and has been an experimental plant for us in the past. The other is the new one, Chufa, that I just mentioned. Then we we'll be doing a couple of experiments to enable prediction of accumulation rates of this refractory material. We've got to have a little room for latitude because it's an experimental program. We're looking for ways to solve problems that we don't know the nature of the magnitude of yet. And finally, we need to estimate the size and the parameters of the many cells that would be constructed and operated, so that there are a large number of interacting components that need stepwise solution. And finally, using that information gained in the individual steps to synthesize it to a preliminary design and feasibility analysis and identify any missing components. So the real tough problem is that you've got to develop an experimental insight into cycles that take a long time and many repetitive cycles to complete before we can detect limiting factors. Early in the research program, we're going to look at critical coupling of systems and identification of critical coupled experiments that may assist in defining a system that can be tested over a short time. And the result is, if we get that, we get to green the galaxy. Thanks very much. Any questions?
One question.
Yes.
Have you ever looked into using bamboo as a band?
No, we haven't looked at bamboo because bamboo has got a lot of refractory stuff in it. Bamboo stems have lots and lots of lignin, which is very tough to break down. So we like to have things that have relatively low lignin content because they're easier for us to chew up and digest.
Because the reasoning behind that would be it's both edible for animals and humans, and it's very stable because you can use it for construction. And it's really stable, actually.
Yes, that would probably be an ideal thing to use on Mars, where you have lots of carbon that's relatively easy to get. You just get the carbon by pumping the thin Martian atmosphere into your habitat. And what you point out is very true. Bamboo is a superb material. Gary?
Are you targeting a microgravity environment for this system, or planetary surface? Or are you
I'm glad you asked me that question. We are targeting that's a very good question. Yeah, I suppose. There actually isn't very much machinery in this setup. There's, there's some plumbing and there's some water, water pumps, but there's not a whole lot of fancy stuff. There's trays and light distribution system, but there's not a whole lot of other really fancy stuff in this system. It's dirt simple. Yes?
That goes along with my question is, what type of lighting are you planning to use? Is it artificial, is it natural?
We can probably get away with either one, but